I was not eaten alive for the last story, so you're getting another one. Skip to 10 minutes if you just want to see the funny helicopter plane fly and hear me say the word procession a lot, while I grapple with explaining how I think these things work. Still here? Alright. Warm up your time machines, because for this one, we're going to be making just a little bit of a jump.
Aside from school, Tenra had never made much of an effort to integrate me. I suppose he didn't feel it was his business, or maybe Mom had told him not to. Hell, maybe I told him not to. I don't remember. But for those first couple of years, it was like being raised back in the CCR, albeit by an awkward, bumbling alien parent, like the two of us were out of a Spielberg knockoff. I didn't think much about him. Of course I didn't, I was 9. To me, he was a weird god trying to masquerade as the one I'd known. But something changed when I brought up the festival. I think I got to see the person Mom had liked so much. He cared for me until then, sort of like I was a very needy roommate who was scared of the dark. But it was then that he'd started to raise me. I think maybe it was the first time he felt he had something to offer. You see, Uncle Tenra fell somewhere on the grand ethereal web that stretches between all of the galaxy's preeminent scientific luminaries and all of her bravest and most ingenious rednecks. You wouldn't know what to look at him. He's bookish, and before me anyway, made a modest living working on high-pressure systems and space stations. Not glamorous work, but shockingly dangerous and sophisticated. He said it took him all over the settled galaxy, past the furthest reaches of the affiliate's borders. Said he'd worked, lived, and made friends everywhere from the glitzy commercial centers and Thika Zone rings to far-flung research stations where the only light comes from the ones you switch on. Deep down, I know I took that life from him. I'd feel worse, but it was that winter that he and I started to figure out how to make do with the situation we'd found ourselves in. Again, Tenra Kalrik, high-pressure systems expert, fell somewhere on that spectrum between rocket scientist and ambitious redneck. And unbeknownst to Mom, or myself before then, he'd been in and out of the Jakagari since the first time he'd picked up a vacuum pump. And more than all of that, he had a project. It was an old project and a crazy one. For years his travels had kept him from it, and its fruition was long overdue. Now, in case you aren't from around here, as I hadn't been, I should spell a few things out. To state the obvious, Lapsa don't celebrate Christmas. As a kid, that sounds like a fate worse than death, but believe me, you get used to it. Tenra tried his best at first. I was 7 years old that first year without Mom, and the presents and tree, even if it was the wrong sort of tree, were flotsam that I could cling to while everything I knew sunk around me. But that morning, I held the toy boat he'd given me and cried because it hadn't come from her. And he cried too, he says, because she couldn't give it to me. To date, he insists I didn't hurt him, but I know I did. Lapsa struggle to hide their emotions. We tried again anyway the next year, and maybe again the year after, but it wasn't doing either of us any good. But still, despite what Rankin Bass Productions may have led you to believe, the Lapsa, while ignorant of Christmas and any of its true meanings, whichever they may be to you, are not joyless people, nor are they without their own Dickensian romance. It turns out that all of us have to make light of the winter famine in one way or another, and for them this means Kaishel Venkenna, the Festival of Storms. Parts are kind of familiar. You've got snow, of course, and you've got themes of generosity and togetherness, but speaking precisely, the Festival of Storms is dedicated to nomadism, an acknowledgement of the need to move on when times are tough, and a celebration of the joy to be found in the places you go and the people you meet when you do. You want to give it a shot? There are 2 parts to the Festival of Storms, a celebration and a race. Let's start with the easy part. Have you ever seen Planes, Trains, and Automobiles? You know that movie where 2 guys are struggling to get home for Thanksgiving or whatever and have to learn to like each other? Imagine if, instead of trying to get to the holiday, that was the holiday. That's the gist of it. There's a whole week this goes on, so you pick a day, grab a case of beer, and then you and as many strangers as you can rally to your cause try to get somewhere or find something. Along the way, you make friends, get sloshed, and probably have a big potluck or something and forget what you were looking for in the first place. It's a suburban mother's worst nightmare, and one hell of a Saturday night. Weird, but no weirder than shit like Murray Lewid. But then there's the race, and let me tell you, Lapsa take this shit seriously. Like NASA rolled up to a soapbox derby, seriously. When Kuarva Akage became the first lapser to break the sound barrier, it wasn't flying a fighter jet or a rocket. She did it test flying a racing plane built for the Festival of Storms. So if you're an aerospace company or a member of the Jakagari, it's like if NASA was a club, don't worry about that, then the festival is a proving ground and showpiece. If you're an ambitious redneck, it's both the highest goal and purest thrill you can concentrate into a few days' time. You see where I'm going with this? Anyway, when fall came in my second year of school, I told Uncle Tenra that I wanted to try the Festival of Storms, and he lit up like someone dipped him in kerosene. It must have been late autumn when I asked about the festival, which I say because I came home from school to find the film of ice on the pond from that morning hadn't melted. Like always, Tenra was there to greet me with a bark and a mug of a sort of sweet beetroot mash that I was fond of. Needy roommate or not, we had a rhythm. I felt safe with him. He knew what to say when I missed Mom, and I always liked the way he'd ask me about school. He had this casual bar-top parlance like we were equals. Come to find out later that Laps are careful about each other's business, and it was only because of a book he'd read that Tenra had known to ask me at all. But the way he thought to do it meant a lot to me, and that day I answered very plainly, as children do. I wish we celebrated the Festival of Storms. He looked confused. You do? Santa can't get here anyway. Who told you that? Velky and I figured it. It doesn't make sense. I probably should have figured out Santa ages before then, but consider, I had a talking space fox for a foster father. Tenra shrugged. Your mom asked me to keep the Santa thing up until you asked, but there's more to it than him, isn't there? Is there? I had some idea of who Jesus was, but I also had a point to make. His brow furrowed. Something about the belief your people were created and forgiven for something? I don't know. It's a big deal, though. It was my turn to shrug. I don't know either. He considered that for a moment, grooming his muzzle with a paw, and then he grinned. You're sure? A steady twitch in his tail betrayed how badly he wanted me to say yes. Suffice to say, I had no idea what I was getting into. You see, I thought the race was something you watched. Purview only of the elite pilots and engineers who made household names of themselves. I thought the Festival of Storms that Tenra and I would celebrate would be the potluck thing. I thought that was what I wanted. It made for a confusing ride to the airstrip, especially when this festival, as far as I knew, was still the better part of a month off. Tenra called his machine Kara Harshi, a word that meant the sound of your blood thrumming in your ears when your heart is pounding. I could neither write nor pronounce Kara Harshi, and learning its meaning came to call it heartthrob. At the time I didn't know that term wasn't as literal as its Kinnery equivalent, but I've come to think it's suitable anyway. Sue me. I introduced Kara Harshi by its name because even now I struggle to find other words to describe it. If biblically accurate angels were a mess of eyes, wings, and whirling discs, then Kara Harshi must have been a biblically accurate airplane. Even by Lapson standards, it's tough to put it in clearer terms than that. I'll describe how it works, and you'll understand then, but for a quick simile, as a way to show you that thing my kid self saw, that's the best I can get you. And if you'd been there, you'd understand why I believed in Santa for so long. If that flew, why not reindeer? But the Kara Harshi I met that year wasn't flying. Not yet. It loomed like an obelisk in the back corner of a tall but otherwise unassuming hangar on the northern end of the Kar Viken aerodrome. Its fuselage, then bare metal, shone gold in the amber of an old bulb that hung from the ceiling. The rotors cast long, twisted shadows, at least until Tenra snapped a switch on the floor and bright shop lights buzzed to life to banish them. What do you think? He asked, genuinely anxious for my word on what he must have considered his most breathtaking work of art. It's cool, I said, still not totally clear on what any of this had to do with the potluck thing. He took it in stride. Tenra once told me that a Lapsa chooses their star name on the day they finally know not only that beauty can be found everywhere, but also all their favorite places to go looking for it. It wasn't that I didn't feel anything, standing there looking at that thing my Uncle Tenra had built. I meant what I said. It was cool. Like a race car or spaceship. And somewhere deep down, I recognized that part of him was burnt into that machine the way part of me was in the macaroni portrait I gave Mom when she was sick. But Mom was a spacer, and I had been born one. We lived on stations and transports. Morning, noon, and night, when I looked out my window, I saw stars. And they were beautiful. Crystalline dots on inky black. Golden planet shine on solar panels. The perfect serenity of the helmsman, coffee in hand and feet propped on the glare shield. And I know Tenra must have loved these things too, for all the time he'd spent out there before he was saddled with me. But before Athika, before the festival, before Karaharshi, I hadn't felt the slick of oil on polished metal, or shared my deepest secrets over wrenches and beer. I hadn't lit a jet like it was a barbecue. I hadn't spun the world in my fingers, heart pounding in my ears. I hadn't tasted the rain and the clouds. I hadn't gasped for breath. It wasn't until he brought me to that place, brought me home, that I saw my first deep blue sky. And that concludes Masterpiece Theater. So, to quote that supersonic speedster rocket J Squirrel, here's something we hope you'll really like. What the hell is a Karaharshi anyway? Well, Karaharshi, aside from being the passion project over which an alien HVAC specialist bonded with his adopted human daughter, is the pit special of thrustwings. Built for racing and aerobatics, it's a coaxial design driven by cold tip-jet nozzles mounted on the rotors and supplied by bleed air from a single central turbine, much like the rotodyne or jet gyrodyne concepts on Earth, or any other tip-jet helicopter that pleases you. It's fast, for a thrustwing anyway, and manages to have just enough range to be useful. But the headliner? Karaharshi is equipped with a cyclic. Having cyclic control, that is, control over the incidence of each blade individually while the rotor rotates, means two things. One, Karaharshi in VTOL mode isn't just a passively stable tailsitter, but a fully functional helicopter. And two, it can do this. As a result, Karaharshi is, despite appearances, not only the most fun of my thrustwings and the most extreme in capability, but also the only one not to be a complete death trap. It's in fact so not a complete death trap that I think I could actually work up the courage to fly it if it existed. But all of that begs a more fundamental question. What the hell is a thrustwing? Well, in the last video I did on the subject, I called them, quote, hybrid rotor aircraft, not realizing that they kind of sort of have a proper name, coined by one Erich von Holst, a German physiologist who tinkered with ornithopters, and, at least on our planet, seems to be responsible for introducing the thrustwing concept sometime in 1940. And in a way, thrustwings are a sort of ornithopter. As the name implies, they're aircraft that derive both their lift and their thrust from their main wings, just as birds, insects, or mechanical ornithopters in real life, Flyout, and even the funny worm movie do. The difference is, thrustwings accomplish this with more conventional axially rotating rotors rather than reciprocating wings. Effectively, they're helicopters, just with enough blade area to use their blades as a mix of wing and highly pitched propeller in forward flight. Why do this? Couple of reasons. If it's 1940, the advantage is that you don't have the material science or jet technology to do VTOL the usual way, and this trick seems about as good as the rest of the wacky ideas for VTOL that people are coming up with. But if it isn't 1940, there are still some reasons. And the first one is still VTOL. Sure, you could build something like a Harrier or an Osprey, but that means getting your propulsion system to give you a thrust-to-weight ratio of at least 1.0 and change, and that is not trivial. And after that, you also need a way of converting your vertically optimized propulsion into forward flight optimized propulsion, which probably also needs to be optimized for a much higher speed. And that is not trivial either. Not that I would suggest thrustwings as a trivial alternative, they are absolutely not trivial, but depending on what you have to work with, I can see some value. While you will technically still be reaching a thrust-to-weight ratio over 1.0 thanks to your rotor, you don't have to deliver that energy nearly as quickly as a jump jet would. Instead, your propulsion comes from way out on the tips of your blades, where the nozzles have a ton of arm and thus leverage on the rotor, meaning that you can turn it with a lot less raw thrust than you would think. How is that different from a traditional helicopter? From an energy perspective, it isn't different at all. A traditional helicopter accomplishes this with a mechanical gear train. But if you think about it, that's what we're doing too. Driving a very large gear, our rotor, from its edge, and trading RPM, or raw speed in the case of our nozzles, for torque. And we can afford to do that because we don't need a very high rotor RPM to reach that 1.0 thrust-to-weight ratio and lift ourselves vertically into the air. That's how a conventional helicopter manages to climb vertically and hover on the same ubiquitous Lycoming O360, from which we're lucky to get 750 feet per minute climb in our instructor-laden Cessna 172s. But helicopters are committed to this solution. Torque is what they're geared for, and torque is what they have. You could get around it, or try to get around it, by mounting some conventional propulsion to your helicopter and building a compound helicopter like Airwolf or an autogyro. But that won't save you from things like retreating blade stall, asymmetric lift, or even just the raw drag of your rotor. For as much fun as the Airwolf intro is, the unfortunate reality is that rotorcraft have a lot working against them when it comes to trying to obtain high linear speeds. But that's thinking about rotorcraft like Airwolf, or Rotodyne if you're feeling slightly more realistic. What if you did something else? What if, instead of trying to make your helicopter fly forward, you just tilted it forward and kept tilting it forward the way you normally would with a helicopter, and increased your blade collective until your rotor was producing all of your forward thrust directly? After all, you can't have retreating blade stall if there is no retreating blade. That's even nominally true of the asymmetric lift problem, though the big asterisk on that is that it will only be true at angles of attack that are close to zero. Asymmetric thrust from propellers due to a blade that's moving overall more upwind than the other is absolutely a thing, and in fixed wing we call it P-factor. That is totally going to be involved, and we will be coming back to it later. But for now, point is we've solved most of our rotorcraft problems by just pivoting our helicopter over until we use the rotor entirely for propulsion, and just like that, we have reinvented the tail sitter. Now, there's still that matter of torque versus RPM, but from there you can imagine what would happen if you just kept increasing the collective on that rotor. Sure, you're kind of limited in the RPM department, but if you just keep increasing the blade pitch, the rotor can keep doing work on the air even at those low RPMs, and make as much use of the torque you have as possible. But we're not out of the woods yet. Now that the rotor's busy facing forward all the time, we need some other way to support our aircraft, and that means wings. Adding wings means adding drag, and we've already got an awful lot of that from our rotor. Not that this sort of arrangement can't be made to work. The XF1 Pogo is a clear example of it in real life. But what if you could arrange to use the blades themselves for lift instead? There are drag and weight advantages there if you can get away with it. As with ornithopters, if your source of lift is also your source of thrust, then you don't have to waste any additional drag on adding one or the other. And in theory, we can have a pretty big rotor without it becoming a burden in forward flight. And now we arrive at the centrally driven thrust wing, a concept resembling Holst's early models. Unfortunately, as much as I would love to experiment with centrally driven designs, Flyout just doesn't offer us a good way of doing it. We can't drive these passive spindles with engines. But on the flip side, tipjet designs have advantages all their own. The obvious one, of course, is that they have no express need for an anti-torque mechanism or coaxial rotor. But there's another, and that is that they aren't committed to making the same RPM for torque exchange that a helicopter or centrally driven thrust wing would. This might be a little confusing since we're working with jet nozzles and not a drive gear like on a helicopter, but our tipjet thrust wing trades the linear speed of its jet nozzles for torque much the same way a small drive gear trades RPM for torque. Our rotors produce incredible static thrust, but like the lower gear in a car, that thrust falls off very quickly as we speed up. We can help with that by increasing the pitch of the rotor as we discussed, but tipjet thrust wings offer a further optimization. Our tipjets produce relatively little thrust overall, but that thrust that they do produce falls off far less quickly with speed than our rotors. Since our tip jets are mounted on the blades, the more we pitch the rotor, the more the tip jets face backwards. The more the tip jets face backwards, the more of their thrust gets used to generate forward speed for the aircraft, and the less gets used to generate RPM for the rotor. Even if our tip jets produce far less thrust than the rotor standing still, say a thrust-to-weight ratio of 0.25, they might produce far more thrust than the rotor at, say, 300 knots. Depending on the design of the jet, their actual physical thrust won't have gone up, but it will have gotten a lot harder for the rotor to produce the same thrust at that speed. So, by using our nozzles increasingly for forward speed, we get to gradually stop using them for torque, and instead use them for what they're best at, producing a nice steady cruise thrust at high speeds. It's handy to have this option, because even if we can increase the pitch of our rotor blades, there's nothing we can do about their twist from root to tip. We can only really optimize them for one speed regime, and that speed regime is spoken for. We need as much thrust out of the rotor as we can get when we're transitioning from vertical flight to forward flight, as that is when we need to keep our angle of attack as low as we can. We'll get into why later, but for now just know that it's critical. That means we can't afford to optimize our rotor for cruise at high speeds. So when we're sitting at 300 knots of forward speed and trying to accelerate, our rotor is probably twisted far more than we would like it to be. By transitioning to using the jet nozzles for thrust instead, we can avoid relying on that rotor at those high speeds, instead simply using it as a wing that windmills in the wind. Truth told, I'm not sure how big an advantage this is, since we will still be suffering from drag due to having less than ideal blade twist, but it's something to think about. All that to say, if you're an alien space fox with a relatively modest power plant on hand and a hankering for decent VTOL performance and decently high speed, then thrust wings are kind of an attractive way to have your cake and eat it too. At least more of the cake than you'd be able to eat if you were building a helicopter or jump jet. Alright, but I said there were reasons besides VTOL. So why besides VTOL? Well, if you're on Earth in the mid-1900s, that's kinda the whole deal. Helicopter technology is still young. But screw Earth, particularly Germany in 1940. I can think of places and times that I would rather be. So, what was Tenra, the alien space fox from the future, after when he designed Karaharshi? Well, he was looking for a somewhat cost-effective VTOL solution, but he had another idea besides that. Just as there's no rule saying that a dog can't play basketball, there is also no rule that says a thrust wing can't have a cyclic. These wings are going to be arranged in a big spinning disc already, he thought. If I could change the angle of each blade the way a helicopter does, I could do all kinds of silly things with my center of thrust. Not only would that make control easier and safer in a hover, and in transition in and out of vertical flight, but in theory I could be incredibly maneuverable in forward flight too. And that is exactly what he did. A thrust wing with cyclic control by definition also has a sort of thrust vectoring, at least so long as the rotor is under load and generating thrust. Rather than change the angle of the thrust using a nozzle, we instead translate the center of thrust using the rotor. Just like with a helicopter, we can use the cyclic to change which part of the rotor produces the most thrust, and thereby attain incredible maneuverability, not just in a hover, but in forward flight also. Alright, so you've got a debatably cost-effective VTOL with a side of thrust vectoring. Is that a good enough reason to build a thrust wing? Well, it had better be, because after that the reasons drop off very quickly into looks cool and makes funny noises. Take your pick, I'm a fan of the funny noises one myself. Now, are there any surprise real-world examples of this kind of thing, like there were with ornithopters? As far as I can tell, not a one. From what I've been able to find so far, it looks like Hulst's own balsa models represent pretty much the only time this has ever been seriously attempted.
Hold on a minute, editing Deco Fox here. This is still mostly true, but I have since encountered a few exceptions that I have to bring up. When I say Hulst's models are the only time I've been able to find it seriously tried, I do mean the models. I am not talking about Focke-Wulf's infamous Triebflügel design, subject of so many late-night History Channel shows. As far as I know, that was never any more than a napkin drawing. But if you want to include napkin drawings, it turns out Focke-Wulf wasn't alone. We had one too. Yeah, there was an American thrustwing, designed about the same time, and being an American design from during the Second World War, I imagine without the benefit of Holst's work. I say we as an American, but really I mean one guy. A Lloyd H. Leonard. I just discovered this guy's patents courtesy of another Flyout friend and a forum post on the Secret Projects forum from like 2005. I have never seen this stuff before, but I am so glad to have found it. It should be keeping me pretty busy in the Flyout department for the foreseeable future. Who is Lloyd H. Leonard? Is he in any way credible? Who knows? The patents are fanciful, to say the least, but I like my aerospace spicy. And it's not like it's any more fanciful than the German versions. But through all that, there's one thing that really stands out to me about Leonard's thrustwing. It's a canard design. Later in this video, I get really deep into the nitty-gritty of what makes thrustwings stable in vertical flight, as I now have a pretty solid theory as to why. For now, the short version is that the tailplanes are very important. But while I'm making that argument, I come to the conclusion that canards might be even better, due to the unique way that thrustwings process. And now I've got to wonder if this exact stability behavior that I've been trying to track down for so long was something Leonard knew about all the way back in 1943. Of course, I've been wondering that about Holst, too, and of Focke-Wulf. That's one of the curiosities that kicked the first video into motion. Was this strange behavior I was seeing in Flyout the secret sauce that made the design seem practical to the people who were working on them at the time? My first assumption was that it probably was. But Holst's early designs seemed to be coaxial, like Karaharshi. They couldn't rely on any source of stability that involved gyroscopic precession, which my theory does. It may well be that Leonard is just going for style points here with his canard configuration, or it's just pure coincidence. But maybe this idea was something that people working on VTOL in the 40s knew about. I really wish I could speak with more authority on who Leonard was and where he might have gotten this information from. The designs, while fanciful, do show familiarity with aircraft. But close as I can tell, filing patents for crazy designs seems to have been kind of a hobby for him. Perhaps the closest one could get to Flyout in 1943, if not possessed of the resources to build your wacky designs for real. Other than the patents themselves and a few candidates for what might be his obituary, it's not a common name, but it's not uncommon either, that's all there seems to be on the internet when it comes to him. More on this theory of mine in about a half hour. Sorry for the interjection, but there's a lot to cover here.
Somewhere out there is probably a model airplane builder who's got bit by the same bug that I was, so I wouldn't be surprised to learn that there were flying examples at the model scale. That said, I haven't found them myself. I am considering busting out my old Spectrum transmitter and taking a stab at it, though. Thrustwings, as I mentioned in the last video on the subject and will yet be harping on in this one, have some really odd stability behavior, or at least Flyout seems to think that they do. I'm very curious to find out whether the predictions Flyout is making are realistic, because so far all of my attempts to understand and optimize for them have been based on the assumption that they have some basis in reality. If they don't, then, well, solving the problem of thrustwings in Flyout abruptly stops being a matter of aerospace engineering and becomes a problem of software engineering. Sort of like the aerodynamic equivalent of speedrunning Mario 64. Now, I find that stuff fun in its own right, but it's largely not what I come to Flyout for. That's more the kind of thing that I play Gary's Mod or Stormworks for. But I don't have a good 3D printer on hand just yet, nor do I really have the model building experience to test this the way that I think I would need to. So for now, we're going to go ahead with the assumption that there is some basis in reality, and hopefully sometime down the line there might be videos where I build something like this in real life. At model scale, mine. I wrote Tenra and I admire him, but alas, I am not him. So that's what a thrustwing is, and why, if you were crazy enough, you might build one. From here we'll get into how they work and how you might build one, but first I want to make two important distinctions. The difference between a passively stabilized thrustwing and a cyclic-controlled thrustwing, and the difference between a single-rotor thrustwing and a coaxial thrustwing. To be clear, we are out of Holst's nomenclature territory at this point, as far as I know. This nomenclature is mine, so do with it what you will. Other people might use different terms to refer to the same ideas. Let's look at Karaharshi again. Karaharshi is a coaxial thrustwing, meaning it has two contra-rotating rotors. It is also a cyclic controlled thrustwing, meaning the pilot controls the pitch of each rotor blade independently. Coaxial thrustwings are not necessarily cyclic controlled, and cyclic controlled thrustwings are not necessarily coaxial. That said, a cyclic is a lot more necessary on a coaxial design. This goes back to those bizarre stability forces. We're going to get into a lot of depth on those soon. But here the important part is that contra-rotating rotors tend to cancel out a lot of those forces that would otherwise passively stabilize the thrustwing in vertical flight. This means that coaxial designs, while much tamer and easier to handle during VTOL transition and in forward flight, are actually much less stable in vertical flight. It is possible to design a coaxial thrustwing to fly without a cyclic, and we will get into a few ideas on how, but as a rule, it's much harder. As for cyclics, slap them on whatever you like. My thought is once you have a cyclic, you might as well also go coax, but there's nothing that says you have to. Cyclics work just fine on single rotor designs. Got it? Cool. Let's talk design. The build I'm going to demonstrate here is a single rotor, passively stable thrustwing. I'm doing it that way because it's the most elementary thrustwing possible, and also the most instructive when it comes to building other types of thrustwings. Besides that, at least to my mind, being that it's wholly reliant on those mysterious passively stabilizing forces, it's also the most interesting concept. And further, it's also the one that I have footage of building. The downside of all that? Passively stable thrustwings are the most difficult to build by far. If you're familiar with Lewis scripting and you're just interested in building a thrustwing but don't really care which type, I actually suggest starting out with a coaxial cyclic controlled design. They are a lot more complicated mechanically, and they take a while to set up, but it is also far, far easier to build a successful one. I know that's not exactly what I'm showing you how to do here, but you can probably infer how pretty easily. You're just going to do the same stuff again on a second rotor and have it go around the other way. If you need help getting started writing a virtual cyclic in Lua, I will be explaining how mine work and roughly how to replicate them in a bit towards the end of the video. Okay, at their heart, all thrustwings are a fuselage, one or more rotor spindles, and some sort of joint, I prefer hinges, to control the incidence of your rotor blades. I prefer to approach this assembly as you see here, modeling the whole fuselage as one unit, and then going back to cut out the spindle area in the drum for the spindle, which I make by copying the main fuselage, deleting the extraneous loops, and then inverting the pattern that I used to cut the spindle area to begin with. I then place my spindle in the fuselage, around where the rotor goes, and then place the spindle drum on the spindle. Since I copied the spindle drum directly from the fuselage, they have the same origin. That means I can simply switch to world space and then copy the position values for the fuselage and paste them into the position of the spindle drum. Again, ensure you're in world space when you do this. As long as you are, they will line up perfectly. And that completes our fuselage. Now we're going to stand the whole thing on end. We need to take off from a tail-sitting position after all. While the order isn't strictly necessary, I perform this operation before mounting my wings. If you choose to do it after, just be aware that your axes will be different from mine. You've probably noticed that you can't just rotate Jimmy here, so to deal with that, we pull the assembled fuselage off of him and slap a hinge in its place. We then remount the fuselage to that hinge. From here, we can line everything back up the way it was, and then finally turn the hinge 90 degrees. We're left with a horizontal Jimmy, but a vertical aircraft. His feet probably are sticking out of the bottom, but whatever. Unfortunately, this hack is as good as it gets when it comes to the Flyout editor. It won't be a problem once he's rotated into place. Speaking of, set the default rotation on that hinge so that Jimmy will pivot into the position he's meant to be in when you launch. Then we're good to go. It's rotor time. Now this would be nice and easy if Flyout had radial symmetry like KSP. But guess what? It doesn't! So we will be assembling our rotor manually, and for that reason I suggest sticking to a relatively low rotor blade count when able. I like 3. Fortunately, we will be designing our rotor in a modular way, so we won't have to worry too much about balancing it, and moving to higher blade counts isn't that difficult, it's just a bit inconvenient. This is where things start to get interesting. If you've been wondering why there's still so much video left, you are about to find out. This is the part where we start trying to design specifically for those bizarre passive stability forces. And if we're to design for them, we also have to take a stab at truly understanding them. For this example, I use a pretty bog standard guess and get very lucky, but we've got a whole discussion and more than a few wild-ass guesses on aerodynamics and gyroscopic forces that we're leading up to. I'll try to keep that section towards the end of the build, but not only do I feel it's the most interesting part of thrust wings as an idea, you may also find it pays dividends when it comes to tuning yours to not be a death trap and generally behave the way you want it to. Bear with me. For the purposes of this quick guide, the bog standard approach is as follows. Slap a wing on a joint, and then slap that joint on the spindle drum. Rotate the joint so that the leading edge of the wing is facing along the length of the aircraft. It is easiest to assemble these blades in the fully feathered position. Please note that you cannot connect the rotor blades directly to the spindle. If you do this, they will all rotate independently and not as a single unit. You must connect them to the drum. As a rule of thumb, you probably want your rotor to be about yay big compared to the fuselage, assuming that your fuselage is of minimum thickness and isn't carrying too much fuel. How big is yay big? I don't know, look at it. That's what I do. You could painstakingly measure it if you want, but I typically don't bother. But shoot for highish wing loading, something that looks like maybe 150 kg per meter squared to the Mark I eyeball. My Triebflugel replica, for instance, is 172 kg per meter squared, if I run the numbers. We're going to get into a lot more detail on this later, but for a single rotor passively stable thrust wing, you're going to want to balance your rotor mass with your rotor area while keeping both figures as low as possible. There are 2 main reasons for being conservative with your rotor area, one general and one specific. The general one is a lot of those things that I've been calling weird forces come from aerodynamic effects on the rotor, and if your rotor is too big, they can overpower you. The bigger your rotor, the more rotor mass you'll need to deal with them, and that creates rigidity, which is the enemy. The specific one is twist. As I'm sure you've noticed with propellers, you want your blades to twist along their length to produce the most constant angle of attack possible. This is necessary because the blade tips move faster than the blade roots. The same is true here. The trouble is, we only get a total of -10 to +10 degrees when twisting a wing, and that is not a lot as propellers go. Now, you could get around this limitation by constructing your wing from a multitude of smaller wings, but we would prefer to avoid that. The reason is, using multiple small wings will interfere with the span simulation that Flyout natively supports. As far as Flyout is concerned, your blades would then be many very small wings with very low aspect ratio, instead of one long wing with a relatively high aspect ratio, and that will result in an induced drag calculation that is higher than it should be. Aside from that, for all its strengths, Flyout is still a simulator. It has to run the numbers on these wings on your computer, and it only has a certain number of frames to get that done. It's pretty good at that, but the more we complicate our rotor, the less reliable the whole assembly will be. I prefer to keep things simple. Thrust wings are tough enough to get flying as is. But coming back to twist, the speed of the blade tip is, of course, for a given RPM, a function of the blade length. And that means that the longer our wing, the bigger the difference in speed from root to tip will be, and the more twist we will need to produce thrust evenly. That means the longer our blades, the less we'll be able to twist them as much as we should, and the worse they'll perform. Not only will they produce thrust less efficiently and be less resistant to stalling, but they also tend to be less stable overall. Because of this limitation, for most sizes of thrust wing, you are going to want as much wing twist as possible. That's what I do here. -10 to +10, remembering to rotate the blade again to compensate so that the leading edge of the root is still facing straight down the length of the aircraft, while the blade is in its default, fully feathered position. When you're happy with your blade, mount whatever you intend to use for thrust to the blade tip. You will want this source of thrust to line up with the leading edge at the tip of the wing, so it will be 10 degrees offset from the wing rotation, and thus 20 degrees offset from the wing root. My purpose here is to build the cheapest thrust wing possible, so I'm using ducted fans and a single reciprocating engine. With one blade completed, select the blade's hinge mount and duplicate the assembly and stack it directly to the side of the existing one. Fix the rotation so the blades are parallel and ensure that they are facing the same direction and didn't get accidentally mirrored. This can happen if you inadvertently place your new blade on the opposite side of the aircraft. Once that's been verified, you need to line it up with the others, and rotate it however far you need to evenly distribute the number of blades you have around a circle. I'm using 3, so that's going to be 120 degrees for me. To do this, I prefer to zero the new blade assembly's local X and Y coordinate, since they should be 0 for all blades, and then leave the Z alone. Since we tilted the whole aircraft 90 degrees, our local Z-axis is also our global Y-axis. With the blade in line but offset vertically, I then rotate the wing into place by toggling into global mode and rotating by 120 degrees yaw in one direction. Finally, I can copy the Y-coordinate from the first blade and place it onto the Y-coordinate of the second blade, bringing the new blade into its final position. Then just repeat that for the third blade, or the nth blade, however many you've got. The final step is to bind a rotor collective. You can do this with an input, with Lua, or however you'd like, really. I like my thrust wings to auto-feather, so for a simple design like this, where I'm not using Lua, I just set the default rotation of each blade to the angle that would lay it so that the blade tip is parallel to the ground, and the wing root has a positive 20 degree incidence, and then apply an input of airspeed z to counteract that default, meaning that the faster the aircraft goes, the steeper the blade angle will become. In reality, this isn't a linear relationship and would be better done with Lua and a polynomial, but linear is good enough for our purposes, especially for a relatively slow thrust wing like this one. If you don't want to tangle with Lua, linear will do you just fine. Just know that you could probably squeeze a few more knots out and maybe a little more stability if you didn't use a linear relationship. As for what that linear relationship should be, for a normal speed jet-powered thrust wing, usually between 0.7 and 1. The ducted fan design I'm working with here is unusual in weight and speed though, so it has a different value. And we're good to go. Time to test and almost definitely find out that your thrust wing does not fly at all. Welcome to many hours of my life. From there, you can either guess and check and trust me when I say it's technically possible, or you can follow me into the depths of the gyroscope dimension,
where the simplest things only make sense after you stare at them for about 40 hours. But I've done that staring, and while it's not perfect, I think I'm starting to have a decent idea of what's going on.
I did tell you that I'd put the real technical part at the very end of this guide though, so first, a quick rundown on the part of tuning that isn't related to the minutiae of rotor design. Fly-by-wire. Let's say you got very lucky and your design is near or in forward flight. You probably noticed that it desperately wants to yaw to one side or the other, unless it's a coax. Don't worry, that's perfectly natural. It happens for two reasons: gyroscopic precession and p-factor. Precession occurs because gyroscopes redirect angular accelerations applied to them to be felt perpendicularly to the direction they were applied. Oh boy, will we be getting into that in a few minutes. But for now, it means that your thrust wing will want to yaw more one direction or the other when you pitch it one direction or the other. P-factor, however, occurs when the rotor translates sideways through the air. This can occur because the aircraft itself is rotating around a pivot point somewhere away from the rotor, causing the rotor to translate through the air, or because the aircraft is itself translating through the air. This causes the blade that is currently moving in the upwind direction to produce significantly more thrust than the blade moving in the downwind direction. The faster the aircraft is translating, the stronger this effect. Since your aircraft will be sitting at a slightly positive angle of attack and level cruise, you will always be dealing with a little bit of yaw tendency because of p-factor. I find the best way to fight it off is to apply a corrective yaw input to the aircraft's tailplane that is proportional to the aircraft's angle of attack, which for this purpose will represent the ratio between how quickly the rotor is translating forward and how quickly it's translating along its y-axis. This is a mostly linear relationship, so you can fiddle with it until it cancels out yaw due to p-factor almost perfectly during all phases of flight. Beware though, there's only so much you can do when the aircraft is still slow moving. Try to fly your pitch-over maneuver in a way that avoids high angles of attack for as long as possible. I also recommend some simple negative pitch and yaw rate gains to help rein the controls in a little bit. If you're a mouse flyer, this won't bother you as much, but for keyboards it helps a lot. Also, the bigger your tailplanes and control surfaces, the easier this process will be. And that is it. No more, stalling. It's time to talk about gyroscopes. If you've gotten your thrust wing back into vertical flight and got very lucky with your design, you may have noticed that this happens. Not a one of these designs has cyclic control, and yet they all settle back into this nice, stable vertical flight. And that's great, but, why? Enter what I have been calling the weird forces. At the time of writing, I am genuinely not sure how many are at work, but I do think I have a pretty good idea of who the suspects are and where they come from. The first time I saw this behavior, I was completely baffled. I threw together my original Triebflugel replica with every expectation that the project would fail because the design would never be stable in vertical flight, especially since Flyout, at least at the time of writing, doesn't give us the luxury of downwash on control surfaces. Seeing this happen, though, I was instantly obsessed. So obsessed that I finished that build and several more over the next month or two, and hurried out a video about what, by the end of that marathon, I thought was going on. And looking back, I was maybe on the right track, but I was missing at least half the picture. And I knew I was missing something.
But doesn't p-factor say that the force should be offset by 90 degrees and thus totally useless? Well, yeah.
I just couldn't work out what. Was it the addition of gyroscopic rigidity from the rotor? Maybe that slowed the oscillations down, but how could it explain why the aircraft would stabilize facing nose up? And why didn't p-factor and precession drive it to the side? Well, let me tell you, finding out has been an adventure.
Alright, pardon the change in mic tone again. I think I actually prefer this microphone, so we're going to stick to it for now. Anyway, this used to be a much longer section of video. Like, literally half an hour of me and a friend, with whom I usually harass our mutual dungeon master by, say, hunting for subterranean werewolves and geometrically optimized search grids, desperately trying to figure out how the steel ball self-erecting mechanism in an old Second World War B-3 drift site works, and then determine whether the self-erecting behavior of thrust wings is like the B-3 drift site self-erecting mechanism. If you want the background, watch this excellent video by Our Own Devices, which is probably my favorite channel on YouTube right now. But the short version, let's not worry about what a B-3 drift site is or does. The important part is that it has a gyroscope in it, and that gyro always points towards the ground. It'll do that even if disturbed. It accomplishes this with a little metal ball set in a run on top of the gyro housing. This ball rolls to the low point of the gyro's current orientation under gravity, and gravity acting on the ball applies a torque to the gyro. That torque is then precessed by the rotation of the gyro, and somehow this process results in the gyroscope slowly spiraling to upright. Our thrust wing seems to also slowly spiral to upright, and it seems to do it because of a constant torque from p-factor that doesn't care about the rotor's current orientation. Could it be the same thing? To answer that question, we would need to understand how the B-3 mechanism worked. And I have no idea. I don't know, my friend doesn't know. Trying to research the things, you'd swear that style of erecting mechanism was some kind of secret alien technology not meant for public knowledge. We've clearly been using it in production since the 40s, but the only traces I've found of it existing are A, the gyroscope theory and applications by James B. Scarborough, 1958, B, 2 patents in the US from the mid-70s, and C, an archived article from the U.S. Naval Institute magazine by one Ensign R.E. Gilmore, U.S. Navy, 1912. None of these sources describe how the device works. Scarborough describes a roughly similar device on naval gyrocompasses, but not in a way that I've been able to decipher yet. The patents? Those just say that the device, quote, erects the gyroscope in a spiral pattern characteristic of ball-type erection mechanisms. You know, like everybody and their grandma has a ball-type erection mechanism. My friend and I argued this for days upon days, throwing out all kinds of esoteric theories about drag, conservation of energy, etc. Our final conclusion was that there had to be something going on inside the mechanism of the B3 gyroscope that just wasn't obvious from outside, and we were missing some crucial part of the picture. Just to defend that conclusion a little, it wouldn't be enough for the device to just tip towards the ball and precess. It should precess infinitely in that case. The force of gravity on the ball would just turn 90 degrees, end of story. The ball must sit slightly ahead or slightly behind that low point if it wants to apply any force perpendicular to precession. So maybe it sits behind? In the B3 mechanism, there's this little friction arm that seems to retain the ball. So maybe it holds the ball behind the low point, and that's where we get the force. But no, it can't be. The direction of that force, when precessed, would be wrong. It would face away from the device, not toward the center. The only way it could make sense, at least as far as we could figure, is if the friction arm held the ball ahead of the low point rather than holding it a little behind. But friction and gravity alone couldn't explain why the ball would stay ahead of the precession. We figure that's what's happening, but there must be something extra going on with that little friction arm that we can't see. I found it. After all this time, I found it. It was hiding in another patent. March 3rd, 1970. Filed by the Whittaker Corporation in 1966. Patent US 3498146 alpha. Quote, this can be accomplished with ball-type erection systems in which the container for the balls is rotated in the same direction as the gyro, but at a much slower speed, and has ball-detaining members about the container periphery. When the gyro tilts, thus tilting the rotating container, the balls roll to the low side where they are engaged by the detaining members and transported toward the high side by the container rotation. As the balls reach the high side of the container, they roll free from the detaining members and roll again towards the low side. The arc through which the balls are transported by the detaining member is roughly centered 90 degrees from the direction of tilt so that the average resulting torque produced by each ball is in the quadrature relation to the direction of tilt to cause the erection of the gyro in a direct path. Wow, that actually genuinely makes sense. I have been looking for this information for months. This isn't exactly what's going on with the B3, since the B3 has only one ball and one apparent detaining member, but it seems to be entirely the same process, so I am satisfied. Okay, cool, we understand. So then the question, is thrust wing stability related to this behavior? If you squint? To summarize my understanding of this system, let's assume that our gyroscope is turning clockwise and is rotated, say, 20 degrees to the left. The balls will roll to the left side, and they'll be engaged by teeth on the outside of the drum, and then they'll be dragged forward and lifted up in a clockwise motion until they roll free again. Accelerating the balls in that way will create a torque that attempts to rotate the whole assembly forward, but precession from the gyroscope will cause the force to be applied to the right instead, which is the direction that we need to go. So how does that compare with P-factor? Let's assume that our thrust wings rotor is also turning clockwise and that the aircraft is also tilted about 20 degrees to the left. Now the rotor in the dorsal position is experiencing more airspeed than the one in the ventral position, and producing more lift as a result. This would ordinarily torque us forward in pitch, but instead the force is precessed, and it torques us back to the right, which would in theory stabilize us. So, is it the same thing? It depends on how much detail you want to get into when it comes to the force in motion. Principally, yeah, kinda. but mechanically they're extremely different. All of that said, pre-edit Deco Fox is about to go on a modest rant about a mechanism that is both simpler and, from testing, seems to be more important than this. But for now, huzzah, we've solved the B3 mystery. And let me tell you, it is a relief. This has been driving me absolutely nuts. There's good news. Our suffering is at an end because thrust wings aren't gyroscopes with erection mechanisms. Thrust wings are tops. Yes, the kind you spin with your finger. Hear me out. You know what kind of gyroscope self-rights? A top. You know why it self-rights? Turns out that's kind of a complicated question. But as I understand it, it arises because friction acting on the tip of the top as it precesses in a circle applies a force to the top below its center of mass, and therefore applies a torque to the top. That torque is in turn precessed by the top's spin, just like any other torque applied to the top would be, and the result is a torque that counteracts the top's present offset from the vertical axis and slowly guides it to the erect position. More or less, anyway. I'm still fuzzy on the particulars. It's pretty easy to prove, though, because tops don't self-right if you spin them on ice. But thrust wings don't have a tip, do they? They don't spin on floors and tables. Ah, but they do. Just as a precessing top encounters friction at its tip, a precessing thrust wing encounters drag on its tailplane. This drag applies a torque to the thrust wing, that torque gets precessed by the rotor, and we're left with a very gradual righting force. Our thrust wing spirals slowly into the erect position, just like a top. So, after everything that's gone into this, and all of the days of research and discussion, why am I so sure that this is what's happening? Well, it's because if I rip the tail off, it doesn't happen. It behaves exactly like the top on ice. Watch these two thrust wings. They are identical in design, and comparable in mass and the distance between the center of mass and rotor. I added weight to the ring down there to make up for the removed tailplanes. When I hit these examples with a disturbance, courtesy of a gust of wind, we see something interesting. Both examples are knocked off angle and into this swooping boomerang-like motion, and that motion gradually develops into a slow circular precession. But past this point, their behavior begins to diverge. The tailless thrust wing settles into this nice stable precession with its nose about 20 degrees below the vertical axis, and it rides that all the way to the ground, never leveling out along the way. And this is exactly the sort of behavior we would expect from a free gyroscope, and saw from the top on ice. The tailed thrust wing also settles into a precession, but unlike the tailless design, the angle of that precession slowly, steadily decreases. This is not a fast or powerful process, but the difference is evident. Oh, and what's that ring on the bottom for? A couple of things. One is to give the thing something to take off from when I pull the tailplanes off, and also a source of weight to counterbalance the reduction in weight from the tailplanes. But two, it serves as a way to lower the aircraft's overall center of mass below its original design. Why did I do that? Bear with me. I have been working on this video for months and only just now figured out this whole top thing. For a top to precess, its center of mass needs to have an arm on the pivot point so that it can hang out over the side to generate torque. That means that we need our center of mass some distance behind the rotor. A head will probably work too, but I haven't experimented much with that. All of this means that the strength of the top-like righting effects scale with the distance between the center of mass and the rotor. Hold on. There's something off about this pivot point thing. Let's take my assertion that it helps to have the CG low. The aircraft rotates around its CG, so I don't think it's really accurate to say it's hanging over the side like a top's CG does. From the previous demonstration, I'm pretty confident that the top analogy is sound. You could see it behaving that way, and failing to stabilize when its source of drag, as analogous to friction, is removed. But I'm not sure how to describe the thrust wing's exact flavor of this phenomenon. I think what's happening is the aircraft is trying to become dynamically stable, or dynamically unstable as the case may be, in the direction it's currently moving, the way an arrow would. Like if we were sitting here in a hover and started to tilt forward, we'd start flying forward too, like a helicopter. As this happens, the tailplanes produce more and more drag, and that wants to pitch the aircraft further forward. But instead, precession demands the aircraft yaw, and that's how we start precessing. If I'm right about that, it means that what the top effect really scales with is how dynamically stable or unstable the aircraft is, as opposed to the distance between the CG and the rotor. But take a look at this diagram. Here I'm assuming the thrust wing is dynamically stable, that the nose will try to lead the tail when it's moving. But look at these vectors. With the drag coming from below the CG and working opposite the precession direction, the force of drag would try to tilt the aircraft forward tangent to its precession, and conservation of angular momentum would instead demand that it be torqued toward the center of the precession, since that's the direction our rotor is turning. If we really pivot around our CG, that would make our problem worse, not better. And as it turns out, on my tests with nose-heavy thrust wings, I've seen that sort of behavior occur, with the aircraft slowly tilting away from center rather than toward it. So it seems like it is necessary for our thrust wing to be tail-heavy, such that the tail tries to lead when it moves, whenever it's in a hover. Fortunately, the moving center of pressure makes it pretty easy for us to be tail-heavy in hover and nose-heavy in forward flight. Looking back, I noticed that all of my thrust wings have been, so I guess that checks out? Let's see what those forces look like if we assume we're tail-heavy rather than nose-heavy. And yeah, those directions make a little more sense. Now the tail tries to lead, tilting the nose in the opposite direction we're precessing in. When we rotate that 90 degrees, thanks to our rotor, that helps us point the nose upright. That's the behavior we see. Okay, cool. But now we have an even bigger question. If we need the hovering thrust wing to be dynamically unstable in order for it to become erect, why did removing the tailplanes hurt the stability rather than help? The difference is plain to see, but shouldn't adding the tailplanes push the center of pressure further back and make the aircraft more stable? And, yeah, good question. I wish I had a better answer than I do. My guess is it has something to do with how far the center of pressure moves as the thrust wing slows down in vertical flight. The slower it gets, the less effective the tailplanes are, but the rotor remains unstalled because it's rotating, and provides pretty consistent pressure regardless of the thrust wing's speed. Past that, in order for the whole stabilizing like a top thing to happen, we need the drag somewhere with a lot of arm. I think that's what the tailplanes do for us, and why removing them ruined the effect. But if I'm right about all of that, you thinking what I'm thinking? A canard pusher thrust wing should give us the best of both worlds. Alright, be right back. Huh. Well, that's interesting. Well, as much as I'd love to go on another month-long tangent for me and 45-minute tangent for you, I think this video is plenty long as it is, and I think I'm going to leave investigating this until a later date. Full disclosure, this is a very brief clip representing about 45 minutes of investigation. During that time, I tried doing a full canard pusher build like I was suggesting, pushing the rotor all the way to the back and relying on front-mounted canards for maneuvering. That is interesting from a hover stability perspective. It doesn't seem to always work, but there are some conditions it seems to work better, and the big problem is it requires the rotor to be somewhat distant from the center of mass, because we're going to push the center of pressure forward by pushing the controls forward. And there is so much P-factor on the rotor that you really can't afford to have it very distant from the fulcrum, and that creates a ton of issues during pitchover. So if that can be made to work, it is not a problem for this video. So far, it definitely seems like thrust wings with a canard and tail are the path of least resistance. Okay, canard interlude over. Back to the, what were we talking about? Oh, right, the ring on the bottom of the test thrust wing, and the effect of center of gravity on the efficacy of the whole top righting mechanism thing. Back to that. So this top-like righting effect was present on the thrust wing as originally designed, without the ring and the center of mass moved further aft, but it was only maybe half as strong, and that made it a lot harder to demonstrate and differentiate from the other forces at work. But, of course, we've seen that this thrust wing, as designed, is stable, even without the ring. So what are those other forces at work? Clearly this top-like behavior is not the end-all be-all. And sure enough, it's not. Over the course of trying to determine where this mystical thrust-wing self-righting behavior comes from, I developed a whole raft of theories with help from that friend of mine. And I'm quite confident that there are two more forces at work besides the whole top thing. Those two things are, say it with me, P-factor and rotor drag. Rotor drag first. A few of you pointed out in the comments that the righting force might just come from the aircraft falling under the rotor, kind of like a parachute. During the first thrust-wing video, I dismissed that idea. I had discovered that my coaxial thrust-wing airliner wouldn't self-right the way the Triebflugel replica did, and the drag theory wouldn't care whether you had counter-rotating rotors or not. So I figured the righting force had to come from something that the counter-rotating rotors would eliminate. And that is partially true. That's where the whole top thing comes in, as well as the third force we'll get to in a second. But I was wrong to dismiss drag entirely. It turns out the reason my coax airliner won't stabilize at all with both rotors going isn't just the lack of P-factor or precession. It's also that I happen to design the aircraft with an overall center of pressure that sits almost exactly on its fulcrum when the rotors are engaged at a shallow angle. This means that the rotor drag has no way of applying torque to the aircraft. I have since found, with a cyclicless version of Karaharshi actually, that it is possible for coaxial thrust wings to passively self-stabilize as long as they are A, descending, and B, their center of mass is some distance behind their center of pressure when the rotors are in the descent configuration. Much like the whole top thing, this force turns out to be pretty weak overall, but it scales with both the distance between the center of mass and the center of pressure during descent, and also the overall descent rate. For most designs, you want to be descending somewhere between 700 and 1200 feet per minute before you start to notice this taking a meaningful effect. That makes it tough to rely on, but with careful flying, it can be done. And then Force 3, P-factor. Again, back from the dead. Well, as it happens, I ended up covering it in pretty good detail in that cutaway, so I won't waste your time. Short version, in case you're clicking around. I'm pretty sure all that's happening is this. Thrust wing rotates or translates in hover flight. This induces a side load on the rotor. That generates P-factor 90 degrees from the direction of the side load. Both P-factor and gyroscopic precession are phenomena that cause forces to appear 90 degrees off of where we might expect them, but they are not the same force, which means that P-factor is also subject to gyroscopic precession. So as long as our angular momentum isn't too high, such that P-factor can't overcome the rotation resistance, then there should be a sweet spot where our P-factor forces are precessed an additional 90 degrees by our gyroscopic forces. And the resulting force? Opposite the direction of the disturbance, reducing it, hopefully. But I just got done demonstrating quite plainly that thrust wings without tails don't self-stabilize. This behavior wouldn't require a tail, so why even include it? I think it's relevant in edge cases, namely the deceleration of the aircraft when it's in a vertical orientation and translating horizontally. Can I prove that? Not really. This is some stick and rudder Jonathan Livingston Seagull intuition. My reasons are thus. From a physics perspective, I can't imagine any way for it not to happen. P-factor happens, gyroscopic precession happens, therefore gyroscopic precession happens to P-factor. It's unavoidable. And when hand flying, in certain situations I think I can feel it and see it in the lift vectors, but it's tough to pin down. But if that's the case, why is it so subtle? P-factor is clearly an enormous torque, which is very evident if you ever screw up a pitch-over maneuver. And when you do, it doesn't really seem like the torque is getting processed much. If you pick up too much of an alpha, you're going to get tugged to the side, no doubt about it. Well, you combine two rotations by adding their angular momentum vectors. P-factor is applying an absolutely monumental amount of torque, and our rotor just doesn't have that much angular momentum. So is it getting processed? Yeah, sure, a little bit. But the result is less like a desktop toy gyroscope and more like the effect of a propeller and crankshaft on your Cessna 172 when you pitch up and down. Is there some yaw deflection when you pitch? Sure. But if you're doing 120 knots and performing normal maneuvers, your tailplanes are going to massively overpower that precession, and you're never going to get a good look at the forest for the trees. But that's why flight instructors tend to teach gyroscopic precession as a landing, takeoff, and slow flight thing. It's not that it isn't there all the time, but under those conditions your tailplanes are much less effective and the angular momentum of your engine and propeller are proportionally larger. That precession is a whole lot easier to notice when you're hanging off your prop at 40 knots, stall horn ringing in your ear. That's where this phenomenon comes into play on thrust wings. When you're already in a stable hover, and the P-factor forces are very low and much more proportional to your rotor's angular momentum. I think it works in conjunction with the maybe force I highlighted on the chalkboard. The deal with that maybe force is that the center of pressure for a radially symmetrical object, like our rotor, is always necessarily ahead of its center of mass. On its own, that would precess in a way that would cause our thrust wing to attempt to move in a horizontal helix, like a playing card or frisbee, a phenomenon that Alpha Phoenix has a great video on, by the way. But thrust wings, when translated in a hover, don't really seem to move in much of a helix. You can see that force at work, it kicks you a bit off angle, but for the most part, the thrust wing pitches out of its disturbance. And I think those P-factor forces are why. In a sense, they're the difference between a thrust wing and a frisbee. Actually, hold on, genuinely a thought that is occurring to me as I'm recording. Maybe that's why boomerangs come back, but frisbees don't. Both of them experience this center of pressure thing, but boomerangs also have blades. Frisbees do not. Don't quote me on that, though. This is a total ass pull. If it were 2 months and a half hour of video ago, I'd do my due diligence and research, but I don't think this video needs any more rabbit holes. Okay, so practically speaking, what have we learned when it comes to actually building thrust wings? 1. You probably want your center of mass behind your rotor. In fact, further is probably better, insofar as you have the pitch authority to transition into forward flight, and you're stable once you do. 2. The size of your tailplanes matters, and not just for control authority. Your tailplanes will be creating a little bit of drag during hover and descent, and that drag will create pitch and roll torques that will, when processed by the rotor, help right the thrust wing. Does that mean you want the biggest tailplanes possible? Not quite. From my testing so far, it's actually pretty easy to overpower the gyroscopic forces from the rotor if your tailplane is big enough. In this case, your thrust wing might never enter the circular precession it needs to in order to stabilize. So you have to strike a balance here. In general, bigger thrust wings with heavier rotors should both allow for and benefit from larger tailplanes. 3. The stuff about balancing P-factor with gyroscopic rigidity stands, but overall it seems to be less important than the top behavior. So we're not just striking a balance, we're striking two. We need to balance our gyroscopic rigidity, a function of the angular momentum of the rotor, with both P-factor and the size of our tailplanes. And that's it. Doesn't seem like a whole lot in retrospect, but after months of building these things blind, guessing, checking, and checking again, I am thrilled to finally feel like I have some idea of what's going on. Knowing what I know now, or at least think I know now, it will be very interesting to see where my designs progress from here. As much fun as cyclic coax designs like Karaharshi are, I definitely want to try iterating on passive thrust wings with this new insight. I've got some ideas to that end, and I, for one, think Lloyd H. Leonard deserves hearing out. Okay, last thing. This time to quote Bullwinkle, "This time for sure." All of this passive stability gyroscope mumbo-jumbo is well and good, but I promised you a guide on how to build a cyclic like the one in Karaharshi. I'm afraid I won't be taking you on a discovery journey for this one. We'd have to go all the way back to Gary's mod in the Halcyon days of the late 2000s. Once Vans shoes were popular, people still went to the mall, and my C in middle school algebra ass was trying to figure out how to use sine and cosine to control a rotor like my cooler Gary's Mod friends. I have been doing virtual cyclics like this for absolute ages. In fact, they were some of the first code I ever wrote. But in case you haven't, the good news is it's really easy. You can figure this out even if you've never studied trig before, I promise. Fair warning though, this is not exactly a Lua or lamp tutorial. I'll show you some examples, but when it comes to the code itself, there are more comprehensive and probably more up-to-date resources than myself. Besides, this video is already way too long. We are not getting into syntax. To build a cyclic out of math, we first have to know what a cyclic is, so how do helicopters fly anyway? This is pretty common knowledge in sim circles, so I won't belabor it. The short version is that a cyclic is a control in a helicopter that alters the angle of each blade individually as they move around the rotor disc, thereby shifting where the lift is concentrated and controlling the attitude of the helicopter. The common way to do this is with a swash plate, a non-rotating part of the rotor mechanism that can pivot forward, back, left, and right and translate up and down. This plate supports a second, rotating plate that is connected to the leading edge of each blade in the rotor head. The lower plate is static relative to the helicopter, the upper plate is static relative to the rotor. Now let's imagine the pilot pitches forward. The front of the swash plate descends, and it drags the rotor blade in the forward position down with it, giving it negative incidence. Now, imagine the pilot keeps pitching forward, but the rotor rotates some. The forward blade is now over here, above the part of the swash plate that's not as far down, so the rotor isn't as far down either, and now it has less negative incidence. This other blade, meanwhile, has moved toward the forward position, and has more negative incidence. The blade back here, on the opposite side of the swash plate, has positive incidence. You see how this mechanism creates areas of low incidence and high incidence in the rotor no matter which blades are on which regions? That's the key. And the quote-unquote real Karaharshi, the one in the story that is, probably works this way. But we don't have that luxury. Instead, we have 3 fixed pivot points that can't interact with anything. But thanks to LAMP, what we can do is ram trigonometry down their throats. So, how do we replicate that swash plate behavior? Let's imagine the pilot is pitching forward again. Follow this green blade as it goes around, and watch how the pitch input changes as it rides over the swash plate underneath. For simplicity's sake, we'll normalize the values between -1 minimum and +1 maximum. See how the peak values happen at the front and back of the rotor and the side positions read 0? You know what else does that? A cosine. And not just a little bit either. Rotors do us the favor of being big unit circles, so they follow trig laws exactly. So far we've been talking about pitch, but the same can be said for rolling. This time it's the blades to the sides we want to have the strongest values, and the blades to the front and back we want to read 0. So where do we turn? Sine. And that's enough to model the effect of a changing swash plate angle on the rotor. But what about if the pilot pitches forward just a little, or suddenly pitches a lot more? Well, those sine and cosine figures are scaling factors. They tell us how much of a given input should be making it through to a given blade, which is why they're running from -1 to +1. So when it comes to strength, all we have to do is multiply. So that makes sense for one blade. How do we deal with the others? Simple. All we have to do is offset the trig functions for each blade. That front blade is in the front position of the rotor, so we'll treat it as rotor rotation. Blade angle equals cosine of rotation times pitch plus sine of rotation times roll. Simple. Let's say we have 3 blades, since that's what we've been looking at. 360 divided by 3 is 120, so each blade is 120 degrees apart. 120 degrees is 2.0944 radians. Trig operations are typically performed with radians, and when it comes to working with things in 3D space and video games, trigonometry is the water of life, so I suggest just embracing that unit. Anyway, that means our second blade is at rotor angle plus 2.0944, and our third blade is at rotor angle plus 2.0944 plus 2.0944. And that is all there is to a virtual swash plate. See? Easy. Math is fun, kids. It makes the funny helicopter go, and it is much, much simpler than whatever magic is going on with gyroscopes. Whew. This has been a journey, hasn't it? Any survivors? If there's anyone out there, I appreciate your patience. both for getting through the video and for waiting for it in the first place. I did not set out to create a feature-length documentary on thrustwings. Frankly, I didn't think I had that much to say. But this turned out to be quite a subject. Every time I thought I knew something for sure, I'd get halfway through writing it only to find out I was way off base. Every time I thought I had every detail I could possibly hope to find, I would uncover some brand new gold mine. Here I am recording the sign-off, and that Lloyd H. Leonard stuff? I found that stuff yesterday. So cheers. This has been utterly fascinating to work on. And maybe, clever willing, it's at least somewhat possible to follow. Ghost has updated LAMP like 4 times since I started this video, so I have to bring Karaharshi up to date before I can release it, but as soon as I do, it'll be on my thread in the Flyout Discord server. I'd like to come up with a better way to distribute these things, but that's a problem for another time. So I'll leave you with some beauty shots of Karaharshi, and see you in another, shorter video. Until then, I wish you a pleasant voyage, by the light of your stars and the flame of your lantern.